Okay, so hey everyone, thanks for the kind introduction. I run the Collective Embodied Intelligence Lab at Cornell University, and our goal really is to design and build and operate robot collectives that are inspired by swarms in nature. So we look at a variety of mechanisms and materials, from rigid robots and soft robots to natural swarms, because they all represent different trade-offs when it comes to embodied intelligence. Uh, Here we go. So this is a short talk, but I just want to show the techniques or the tool set, if you will, that we think of when we design intelligent task-oriented systems, because there are many ways to achieve intelligent behavior in a single robot, and even more when it's a swarm of robots. And so intelligence can be explicit software and processors, like in traditional robots, obviously. It can stem from careful pre-planning or online learning. And if you have many robots, their global behavior can either go from like a centralized controller or from lots of high bandwidth communication between all of the individuals. But, the theme of the workshop obviously is that it can be more than that. It can be rooted in the particular way that the morphology of the robot hardware is implemented. You can think of built-in reflexes or passive degrees of freedom where compliance is needed. And again, if we have many robots working together, then global interaction can also emerge from direct physical interactions or perturbations between agents that work in close confinements. Or it can emerge from environmentally mediated interactions, which I'll show you more on later. And so I'd say, in traditional robotics, we're very comfortable with the design techniques here on the left, and we're getting much better large-scale distributed communication networks, whereas systems based on the techniques on the right are still much more under development, right? And so my research is really all about the interplay between all of these different design techniques to generate task-oriented behaviors in robot collectives. And so I'm just going to rapid fire a whole bunch of examples at you now that sort of highlights our research on how to mix and match from this sort of toolbox or design toolbox, if you will. And so I'm going to start with examples of how to make intelligent robots by exploiting carefully designed morphologies. And then I'll work my way up to these other kinds of tools. And so some of the strongest examples I've seen of morphological intelligence in recent times stems from soft robots. And I'm sure you've already heard of soft robots in this workshop, so I won't dwell too much on the topic. But just to reiterate, here's a classic example of a soft mobile robot. It consists of two antagonistic polymer chambers in this case that are driven by pumps and valves in that backpack that's sitting on top. And then because of the way the strain limiting layers are embedded into the polymer and due to differential friction underneath the robot, it inches forward with every inflation, and it can turn if you inflate one chamber more than the other. So what's nice about robots like these when we pursue robot swarms is the fact that they're fairly cheap, they're fast to implement, there's little wear and tear, and they're quite robust to physical interactions with other robots. Of course, our goal is to achieve more complex behaviors with less driving circuitry than this terrible backpack. And so here we go. So in follow-on work, which was a collaboration with the Shepherd Lab, we started looking at how you could embed poroelastic foams through these soft chambers. The reason being that now fluid resistance in the small conduits will cause differential pressures throughout the geometry of the robot, at least temporarily, to give it more complex motions. So here you can see like an example of a traveling wave achieved with a single pressure inlet. And then, of course, it becomes a damped traveling wave because the pressure eventually equalizes throughout the body, but you still get more complex motions with a single inlet. In recent work, which is still in review, we've developed legged robots based on that same concept. So each of these legs now is just a series of hollow bellows, which are connected with slender tubes. And just like before, each leg has a single pressure inlet, which is connected to two syringe pumps that are sitting in the robot backpack on top. Now, in terms of design and fabrication and operation, right, the actuators are about as simple as they can be, but we get the super cool organic looking gate. And long story short, we achieve this by carefully choosing the relative timescales between the solid, the fluid, and the input pressure cycles in the actuators. So we've shown that, again, using this technique, so just the single pressure inlet, we can place the tip of the leg or the actuator anywhere within this 2D workspace, at least temporarily. So here's some example gates that span that workspace, just to give you an example. Okay. So those were single robot systems. Now let's look at how this plays out in multi-robot systems. And since time is short, I'm just going to show you sort of two quick examples from either end of the spectrum. Now in one, global behaviors stem entirely from robots with a fair amount of processing power and high-speed neighbor-to-neighbor communication. And then the other one, coordination stems entirely from low bandwidth physical coupling between the agents. So on the left side of my slide here, we developed these planar modular robots that are composed entirely of flexible circuit boards that are just rolled up in a loop. Each module has computation, sensing power, and it has switchable magnets that lets them do relatively high-speed communication with their neighbors. and produce motion when they're coupled with other modules. And so we get basically all the benefits of a modular robot, where the processing power and the degrees of freedom increase when more modules are added. We get, resilience to individual failures, but we also get the benefits of soft robots, right? They're inexpensive, there's little wear and tear, their passive compliance allows them to overcome physical perturbations. And so in the bottom there, you see them navigating through a cluttered environment to find a near optimal path towards a goal, but with entirely distributed computation. On the right side of my slide, we took the opposite approach. So again, these are planar modular robots, but their perception and neighbor-to-neighbor coordination now is limited entirely to strain, which is propagated throughout the collective. Strain is a very low bandwidth medium compared to what we had before, but it's one that comes more or less for free in soft robots, right? And you'll see here that, each robot is just a little inflatable oscillator, yet we've shown that because they're coupled in these tight physical formations, we can achieve collective-wide synchrony, traveling wave locomotion and dispersion by relying on coupled oscillator models. And then upcoming work at RoboSoft, we're also showing how robots can use just proprioception, again through strain, to achieve distributed consensus on, in this case, inflation levels. Okay, so from physical interactions to collectives that actually leverage environmentally mediated interactions. And again, I'm going to show you two examples. So one is going to be on collective construction in a medium that's fairly static, so building material. And then the other one, second one, is one where a task, in this case, swarm aggregation, is achieved through induced pheromone and airflows, which are much more transient than the building material. So here's some old work I did at Harvard in collaboration with Professor Narkpal and Dr. Werfel. In this case, these robots are trying to complete a user-specified blueprint. But interestingly, right, every robot has limited processing power, local sensing, no explicit communication abilities, and so no notion of the overall state of the structure. Instead, the construction process is coordinated entirely through the way that building material is added. The way it works is that we first generate some general traffic directions that robots should follow when they move over the structure. And then from that point on, we can deploy any number of robots that will carry out a reaction-based rule set, which is independent of the particular structure. And so this is a really neat system because, it truly lets us play around with where intelligence belongs in that system, right? Whether it's in pre-planning, these offline compiling steps, or in the reactive rule sets that lets the robots extend this rectilinear world that they can easily reason about. It could also be in the morphology of the robot body again. And just a quick plug for our most recent construction mechanism, which actually allows both single and collaborative modification of dry granular environments. So we're pretty excited about coming up with algorithms to do continuous structures next and really reason about how information can play out through the environment in these kinds of systems. Now, I told you that environmentally mediated coordination doesn't have to work in static mediums. It can also work in much more dynamic mediums. So here's a phenomenon we're studying. This is not in robots, but in actual honeybees. And they'll collaborate to find their queen, who's located over here on the right. And she'll emit a pheromone, but it's in this outdoor turbulent environment, so it's hard to find. And what the bees do is actually allocate a few workers to propagate her signal by exposing their own pheromone gland and then using their wings to drive a jet of pheromone backwards, which other bees can then follow. So this is really exciting because now you're using air as a medium to transmit information, right? And it allows you to not just store and pass information like we did before, but also potentially to amplify and dampen and filter information. So this is much along the lines of what Josh was just talking about. And so basically we've developed a series of techniques to study what these bees do, and we're now working on translating these insights into robotics as well. Okay, so a lot of examples. One final example is a collaboration with Professor Metin Ziti's group at the Max Planck Institute, where because we're now working with actual microscale individuals in a swarm that have no onboard computation, all their collective behavior instead stems from these pre-planned global signals, the morphology of the agents, and their physical interactions. So these are ferromagnetic sub-millimeter disks with small mechanical indentations floating on an air-water interface. And this swarm is subjected to two orthogonal time-varying magnetic fields, so there's a global signal controlling them. But that also means that the disks are repelling and attracting and creating flows as they spin around their own axis, really allowing us to exploit the interplay of hydrodynamic, capillary, and dipole-to-dipole interactions to produce interesting task-oriented behaviors. And so we've shown sort of a wealth of different things here. Okay, so I think I'm coming up on time. So that was my rapid-fire introduction on how to design collective embodied intelligence. Hopefully I've piqued your interest. And finally, I just want to thank all of the amazing students and collaborators and all the kind funding agencies that supported our work. I'll leave it at that. Thank you.
Thank you so much, Kirstin. Really, really fascinating work with all the different mechanisms and ways in which you're communicating with robots through the environment. I was just wondering, one quick question before we'll later bring you back for the panel discussion, but you gave the two examples of the local coordination and then the strain-based kind of other kind of global coordination or other method. Do you think the mechanism is driven by the body or the embodiment of the robot that selects, should this be local, should this be global, the coordination method, or is it our tuition or our basis on it? Is the coordination method driven by the embodied design?
Yeah, so the reason why I'm really excited about the two examples of sort of deformable robot collectives that we have, modular robots, is that on one hand, right, we can apply all of our traditional techniques to it, right? We can do all the planning and all the things that we know how to do. And as we add more robots, we just get more computation power, which is really cool. But on the other hand, right, like it's all about strain. When the little oscillators inflate more, they become softer. When they inflate less, they become stiffer. And so now we can actually try to have robots that actively modify their own dynamics in order to propagate information in different ways. And so it's something that would not happen unless they were physically connected and embodied.
That's fascinating to take communication in so many different ways and start introducing the environment. Really, really fascinating.